Hello everyone, my name is Advait and this is my machine learning project which is air quality index analysis using different ML algorithms. So the air quality index is an environment protection agency's tool that ranges from 0 to 500 that measures the daily air cleanliness and associated public health risk, and higher AQI would indicate that there is more pollutants and associated health concerns. There are six color codes to indicate the health risk. If the air quality is between 0 to 50, then there is good to little to no risk, and you can continue with your outdoor activities. If it is moderate, that is yellow, ranging from 51 to 100, then it is acceptable except for sensitive individuals. If it's in orange, which is 101 to 150, then it is sensitive. Then it is unhealthy for the sensitive groups and children's and elderlies and with those with lungs and heart diseases. If it's in the red sections, then it's unhealthy potential health for the general public as well. And if it is anywhere between 301 to 500, then it is hazardous for any groups and everyone should just sit inside, indoors. So why this matters? Because you can just look into the sky and you might think that the air is clean, but that is not the case. It can contain harmful effluents and harmful pollutants that can affect your lungs, health, and can cause greater risks to your health. So where does this score, this different color-coded scores and the ranges comes from? Well, it comes from these key pollutants, which are listed over here. A few of them are listed here, which is PM 2.5 to PM 10. What is 2.5? It is the actual length of the particular particulate matter 2.5. So it is very fine particles that can affect your lungs and hearts. PM10 is larger dust and smokes. NO2, nitrogen dioxide, carbon monoxides, and SO2 and O3, that is ozone. These are all the factors that determine the AQI levels, and these are the factors that can be used to make the prediction of the AQI. So what are the factors that play a role? Well, there is traffic, your rush hour emissions, car engine emissions, industrial activities, weather conditions such as wind, humidity, temperatures, city designs can be important factors, seasonal changes, all factors could be taken into consideration. The goal of this project is simple. It is to identify the patterns that signal higher air quality risk. The second goal was to predict whether a day is likely safer or riskier. Can you avoid going outside on a particular day? Should you avoid it? Can you delay the task and to when the day is better, something like that. And the goal three is to compare the different machine learning methods that were used and to come up with which one was the best. This was the data. This is the publicly available data on Kaggle, which contains around 16,000 rows. This is the snapshot, which is the training data, which was the training data that was used. So these are the factors. We'll get back to it anyways. So interesting findings is that I run the unsupervised learning, which is PCA, and find out that I only need 7 dimensions to retain 95% of the informations, which was evident from the silhouette scores for k-means and the elbow methods. So from these I got that the best dimensions is 7, which is able to capture 95% of my information. Also, it could an interpretation was that the AQI behavior have discoverable internal structure, so it is not random, and there are some patterns that needs to be recognized by our models and extracted by the model to this is the SVM ensemble, which is the clean data snapshots. Now the AQI, this could be the considered as the label, and these are the factors, the dependent variables upon which the AQI is dependent upon. So all of this, so the end goal is to use all of these factors to get the AQI, and then to label it as 1 and 0. So 1 is hazardous. So as you can see, every single AQI level over here is over, I guess, 200, I guess. So it is labeled as 1, which is hazardous, so you should not go outside on these days. For the different machine learning models, the methodology was the same, is to read the label pollutants of each and every day, train the models on one part of the dataset, that is the training and the testing split. You train it onto the training data, and then you test it on the unseen data, and you get your precision scores, the F1 scores, confusion metrics, all that stuff. And to compare the outputs and to keep the most reliable methods and to extract which method works the best. So the different models have different methodologies. For example, our SVM model learns the boundaries, the trees, the decision trees uses the splits by rules, ensembles combines multiple models, and then take a vote or the average scores. So the predictive performance, the main supervised models that were used, and the results are over here. Logistic regressions, decision trees, naive Bayes, and SVM were used. SVM came out to be the best performing models, and also ensemble based models, in which random forest came out to be the best. Again, in SVM, I tried out the three kernels, which was the linear, the polynomial, and RBF, the radial basis function. Radial basis function came up to be the first, but a key finding over here is that the linear and polynomial also gave competitive results. So it was because of the fact that the data is not completely linear, but it is also not completely non-linear. So a linear model was able to fit the line. I was able to get an accuracy score of 0.91, but RBF shows consistency, which is the best thing, I guess. This comes from the validation set, by the way. The combining models, obviously, ensemble learning was the best one, which made use of the random forest. Random forest, what is random forest? Random forest makes use of multiple decision trees and then takes up voting. So if there are 10 random forests and 9 of them gave a value that it should be labeled as 1, which is hazardous, and only one of them gave as non-hazardous, then obviously the end result would be hazardous. So random forest for the overall between all the single models and the combination of the models, that is the ensembles. Ensembles with the random forest came out to be the best, which having 0.941 as the overall accuracy. I also use ADA boost and soft voting as the ensembles, and again the random forest came out to be the best among all three. This is the feature importance PM10. So particulate matter 10 is the most contributing factor, followed by particulate matter 2.5 and all the other pollutants. So the key finding, the final summary of this is that air quality index and the value associated with it is not a random guessing work. It is an intricate pattern that throws you the value of AQI, and this pattern was best captured with SVM with the radial basis functions as the kernel, and also decision trees, multiple decision trees, that is the random forest. And what it means for everyday life is that, for example, this is a nice tree. This is a nice diagram. So on weekdays from Monday to Friday, as you can see that it is the PM 2.5 concentrate matter is goes beyond 800. So it's just obvious because on weekdays there is more traffic, there's more industries working, there are a number of factors that can contribute towards this, because of which the PM 2.5 matter part concentration is above 800 as compared to the weekends, Saturdays and Sundays. Nobody goes to work on Sundays. So this is not just so the future scale of this project is to scale this into a pipeline for supporting continuous city monitoring, which is like it could make use of something called as the LSTM models or something like that, which can take into consideration the actual the data, which is the PM 2.5, PM10, the current values of it, and then spit out a value of the AQI in real time. The end goal would be to make an AQI dashboard so that it is on your display or lightweight mobile applications that can throw the risk associated with it, and it can also tell you in real time what is the AQI levels that are right now, or to make a prediction based model that can predict the AQI values in the future. For example, in the future next few hours, the AQI is going to be, for example, the API is going to be unhealthy, but in within a few hours it is going to be from moderate to good. So probably that is a good time to go outside, and because health is important. So this was my presentation for my machine learning project. I hope you like it. This is my website where all the diagrams are available. So this is the introductions, the analytics from source to insight, the data collections. This is the API source, and this is the static data set, whereas this is the API from which the dataset is being extracted. These are all the graphs, PCA. This is the 2D PCA 1 and 2 and 3. Beyond this, I don't know what's this like. The clustering. Interesting fact about this is the associated rule minings, which is PM10 very high, and the season is winter. Then what would be the support, the confidence, and the lift for all of these? Then there's rules by lift, decision trees. Uh, by the way, the index uses Gini index. Samples were around 12,000s. Again, here consistent results are there. The important score is PM10, which comes out to be the root node. Naive Bayes. There are multiple naive Bayes models that I've run, and turns out that the categorical and the Bernoulli ones comes out to be the best. SVMs, all three of them are giving are giving good results, but the consistent ones is with the RPF kernel. Regression, linear versus logistic. Again, I think logistic regression is giving more better results than the multinomial ones. So this is all about the project. If you have any questions, you can reach out. This is my website if you want to check it out. So yeah, thank you.